This is CS50, the end of week 2. So I thought I'd begin with a short note that one of your classmates sent to me earlier this week. I'll leave it anonymous, but read the content. Your lecture, I don't normally do this with your emails. Your lecture the other day reminded me of this scene from The Computer Wore Tennis Shoes. If you have never seen it, I would highly recommend it just for the technology. Obviously, it is a little old, but it is funny to see what people thought about computers in 1969. So I give you a scene from The Computer Wore Tennis Shoes.
Computer are input, memory, control, arithmetic, and logic, and output. And I think we can see demonstrated from these charts that man has done a rather admirable job of imitating the human brain. And even though it's an imitation, in many ways the machine we've developed can operate more if we can ourselves. And now, in the past couple of weeks, I've been working on a small experiment, which is intended to show how we can be replaced by a computer.
Hey, this may be a way of getting rid of Dean Higgins.
We live in hope, Dexter. And now, let's suppose that your parents are going away for the weekend, and they leave you the following instructions. If it's raining tomorrow morning, when you wake up, you are to close the windows, open the door and let the cat in, phone the grocer and have him send over the following list of groceries. Right? Well, you wake up in the morning and it is raining, and being the conscientious and reliable young people I know you to be, you promptly forget to do it. Well, actually, I'm sure you would do it. But let's see if a computer could also do it. Now, this is a rain gauge, and it's sitting on the roof of the building. And when the water falls into this gauge, it sends a signal to the logic unit of the computer, which immediately notifies the memory bank of the computer to seek out its instructions for a rainy day. The memory bank, in turn, activates the electronic circuits. The window closes, the door opens, hopefully the cat comes in, and the automatic telephone goes into action. Right? Well, let's see. Rain falls.
This is a recording. Please deliver the following groceries to 445 Annex Street. 1 pound of bacon, 2 dozen eggs, 4 quarts of milk.
Well, it's enough of that. Thank you. Well, so much for the speed of the computer. Now, another very important feature is its infallible memory. Before this computer was owned by the A.J. Arno Company, it used to be employed by the Space Research Center at the Pacific Institute of Technology. And they were kind enough to send us this magnetic tape, which will call forth from the computer solutions to a series of problems that would occur on a simulated flight to the planet Saturn. Now, mind you, it was 20 years ago that this program was operational. 20 years. Well, if you'll watch the center panel, please. Well, it seems like our flight to Saturn will be a little delayed.
In any case, that high school has like $10 million worth of computer equipment apparently in the front of it. Computers don't have so much the same kind of blinking lights. There's an allusion there to memory, which will be a little apropos for problem set 2. For problem set 1, as you may have seen already. What I thought I had not, in fact, seen that clip. And so I did a quick Googling, and that's actually as relevant as the movie really gets, I think, to computing. If you read a quick plot summary here, I'll just give you a little teaser. This is more of a spoiler alert. But you've had 41 years to see this movie. So Kurt Russell and his friends attend a small private college which cannot afford to buy a computer. The students persuade wealthy businessman to donate an old computer to the college. He is the secret head of a large illegal gambling ring which used the computer for its operations. While installing a replacement part during a thunderstorm, Riley, the professor, I presume, is zapped and becomes a human computer. He now has superhuman mathematical talent, can read and remember the contents of an encyclopedia volume in a few minutes, and speak language fluently after reading one textbook. Riley single-handedly leads Medfield's team in victories against other colleges. During the tournament, a trigger word causes Riley to unknowingly recite on television the details of Arno's gambling ring. Arno's henchman, and it just goes on. So an interesting movie, but a fun clip perhaps nonetheless. So a few announcements, and those are one, sectioning. We've had super sections, as we call them, this past week, really available to anyone who would like to attend. This coming week, will we start the more traditional assigned sections. The sectioning tool, the FAS sectioning tool, will be available to you later today. We're just waiting for confirmation on some times. We'll post an announcement to the course's homepage at cs50.net on the top with a link. So if you want to check that after dinner time or so, you can fill that out. And we will close sectioning by this Friday at the time to be stated on the course's website. Inevitably, in a class of this size, we're going to have to make some adjustments. So you'll receive instructions when you get your section assignment on how to deal with unforeseen conflicts if, for instance, some other class just moved you around. If you have been working and are still working on problem set 1, do realize that a good deal of support and assistance is available to you. So this is our little Google Calendar that we embed in the course's website. And this is the number of office hours we have just in the next couple of days alone. If you look at this in graphical format, I mean, it's actually pretty remarkable just how many of us there'll be down there. So it's in Science Center B14, which is you go into the Science Center, you go down the steps, turn left, and there's a pretty big computer lab there. The way the workflow generally works is just grab a computer or bring your laptop. We use the whiteboards alongside one of the walls where you just write down your name if you have a question, and we just go through the list top to bottom, left to right, and cross names off as we go. Realize that there's inevitably a challenge for us in actually helping people in this kind of context, especially as the deadline really approaches. So do view these particular office hours definitely as an opportunity for help, but particularly as an opportunity to work with someone for just a few moments to help get you unstuck or to get you past some stumbling block that otherwise, if you struggled with on your own, you might sink or waste even multiple hours on just something that you're just not seeing. So if you have more conceptual-oriented questions, you can absolutely bring them to office hours, but just realize there's always a crunch time-wise, especially on Wednesdays and Thursdays. So do reach out ultimately to your assigned teaching fellow, to me, to the help list, to the forums online, if you'd like to sit down with one of us more intimately and more sort of tranquilly and work through problems for more than just a couple minutes at a time. So with that said, these forums I'm referring to are these. At help.cs50.net are bulletin boards of sorts, discussion forums, where you can not only browse discussions, questions that your classmates have asked, you can certainly ask questions of your own. If you would like to flag them as private because you just don't want your classmates to see what you're asking, you can certainly do that. And if you're sharing a particularly decent amount of code, you should definitely submit it as private. Or if easier, you can email help@cs50.net. And realize, too, as we say on this homepage here, by default, we anonymize you when you log into this bulletin board, whereby you're all logged in as quote-unquote students. The staff can still figure out who you are in order to help you most effectively, but as for your classmates, they'll just see you and your questions as students. And this is very much deliberate on our part so that you just don't feel that inevitable angst when it comes to asking what you think is a dumb question. Probably isn't, but you don't need to disclose your name. And if you do wish to disclose your name, you certainly can per the directions on this page. So with that said, let me go ahead and mention one other thing. So one of the other features available is a link up top on the course's office hours page that will lead you to what we call the virtual terminal room. The virtual terminal room is really a glorified chat room, but it's a piece of software that you can log into via the office hours page as yourself after logging into the course's website. You'll appear in the top left-hand corner, as I just did, with your actual name so that we know exactly who we're working with. And then what you can do is raise your hand, so to speak. There's a little icon of a hand here at top left. You go ahead and click that. And what happens is we, the staff, see a little blinking icon in the top left that says 1 out of 2 hands, 1 out of 10 hands, or some number of hands. And it maintains in the little row up there your placement in line. So this is pretty much a computer version of the whiteboard in the Science Center. The goal of virtual office hours is if you're sitting down in Mather or the Quad or wherever, even off campus on some weekend, we'll still hold not as many, but some virtual office hours. So you can log into into this, not only chat with us interactively, but on the right-hand side here, which is just a wallpaper right now, you can actually grant us view or control of your own screen. So if you've got PuTTY or Terminal up on the screen and you're having some trouble that's really best seen with in that natural environment, we can actually see sort of tech support style on the right-hand side what you're doing. And you can see everything we're doing. You have to grant us control explicitly. So do keep this in mind as an available option as well. Lastly, that was it. Let me go ahead and, oh, that's nice. Someone learned how to send write messages on the cloud. All right. I'll write you back later. So that brings us back to this. It's a feature that will be disabled by tonight, I'm sure. Well done, though, class. All right. So a couple of, so a couple of FAQs that have come up in section, or rather in office hours. So we keep track of the types of questions that come up, lest I've said something stupid in class or been confusing, certainly. And so what I wanted to do is loop back, at least with a couple of things that we see recurring, and very understandably so. But let's try to clear up a couple of frequently occurring issues. So we've seen a lot of this, for instance, in office hours. And maybe you too have done or are currently doing this. But there's a problem with writing a statement like printf followed by getInt alone. So someone who's a little more comfortable with this at this point, what's a problem here? Or what is the problem?
You don't know where to store it as one.
Yeah, so you don't actually store the return value of getInt. So we'll talk a bit more about this idea of functions today. But getInt, you, again, can think of it as a black box whose purpose in life is to prompt the human for input and pester the human if he or she doesn't actually give it an int. But then once it has that integer from the user, it quote-unquote returns it to you. But if you don't actually do anything with it, it simply disappears. And therefore, it's well done, classmate number 2. The beeping means a hello message. Let's see. Just to illustrate this point, thought it'd be more fun to do this without just me, but 2 of you, if you would like to come up for just a moment. Volunteers, please. Yeah, come on down. And how about in the purple there? Yep. Purple, pink? Yep, come on down. Oh, and darker purple. OK, darker purple. OK, 3 volunteers. I will make up a 3rd role somehow spontaneously here. All right, so why don't you have a seat on the chair on the right-hand side there? All right, and once you have a seat in the 2nd chair, and why don't you come here and wing this with me? So, and what are your names?
Christiana.
Christiana and?
Jordan.
Jordan and?
Karen.
And Karen. OK, so just to illustrate this point, and then we'll actually use this in a more code-oriented environment, suppose that Christiana is a function. Let's call her getInt for today. Jordan's going to play the role of human. And so I have equipped my function with a whole bunch of memory, which we will implement in the form of old school paper. We will equip Jordan, meanwhile, with a keyboard or an old school pen. And now, Christiana, if you would, your goal in your role here, no, let's see. Still trying to work out a role for you, so hang on one sec. So your role here in this demo is to get an int from Jordan. So go ahead and prompt Jordan for an int. Say something like, give me an int.
Give me an int.
All right, so Jordan playing the role of human is going to type or write something down on this piece of paper, hand it back to getInt. So inside of getInt's memory, shall we say, is this in fact int, which is the number 10. It looks at the moment, but we don't know that yet. And here, I finally have a role for you. So now, if Christiana doesn't actually, if I, the programmer, who am programming these little puzzle pieces, don't actually do anything with this return value, and I call getInt, she wants to hand this piece of paper to me. But if I don't actually assign, no, I just messed up the demo. So if you don't actually assign it to something, it falls on the floor and the value goes away. It was a complete waste of time, unless the goal in life was simply to pester the user for some input. So now, if we actually introduce the variable x, welcome x, let's do this again. Let's try a different number just to make the demo more interesting. GetInt, if you will.
Give me an int.
All right, this time we have the number 100. And so this time, when handed back this value, I store it in, we'll say, x. And now we actually have retained the value. So I realized this was among the more childish demonstrations I could come up with to illustrate this point. But odds are you will never again do that on the screen. So a big round of applause for our volunteers, if we could. And you can keep that as a souvenir if you'd like. And if you could just meet up with the teaching fellows for our legal department, that would be great. All right, so there was one other detail. And right. Yeah, right this way. Thank you, number 3. All right. If someone could figure out how to turn off messages, that would be great. This will be an interesting class. So the second common thing that we saw was a syntax like this, right? So write ideas. You're definitely borrowing some of the pieces we've looked at, the curly braces to encapsulate one or more lines of code, the semicolons to terminate lines, the parentheses to pass in inputs, arguments to functions. But if you throw them all together, things tend not to work. All right, and so this is a thing we, number 4, saw very commonly, which was this is something we saw commonly, and there's a couple of issues here. And this isn't to, point out the flaws in someone specific, but to point out some of the common mistakes. So what's one mistake that's apparent to some here? Point out what may to you be the obvious. What is here that shouldn't be here? All right, so we don't need the curly braces. The curly braces, really, we've only deployed in contexts like loops, while loops, do while loops, for loops, where we want to encapsulate one or more lines of code all inside of some conceptual idea, like a condition, like a loop. Here, printf recalls a statement. And just like in Scratch, statements were these one-liners. I think they're purple or so in Scratch. Or, yeah, purple, I think, generally. Say hi for 2 seconds. Right? So similarly, if you've got one line of code with a semicolon at the end saying this is the end of the statement, it doesn't really make sense to continue that conversation, to try to continue conceptually that puzzle piece with the curly braces. Now, as an aside, this may very well compile. In fact, this example would compile because you can use curly braces in this way to encapsulate lines of code, but realize for now that not good. Only use these for conditions, only use these for loops, and it is in fact correct to put the semicolon on the end here, but not, for instance, in a case like this. If I, by contrast, do a for int I gets 0, I is less than 10, I plus plus, and then I do this because I'm in the habit of ending my lines with semicolons, and now I go inside my loop like I learned to do, and I do something. There's a problem with this. All right, so it's definitely the semicolon, but what is the effect of that semicolon, would you conjecture? Yeah, let's go here.
It just ends, it stops looking for more things to do, so it just tries to evaluate the for loop as like
OK, so that's true. It ultimately evaluates that line of code, but just once, the stuff inside curly braces. But the semicolon on the end essentially has the effect of this. Go ahead and define your loop, do nothing, close your loop, and then down here, do something. So in other words, if you terminate these lines early, if you terminate the for loop early, if you terminate an if condition early with that semicolon, the code may very well work. And this is a common source of frustration and conundrum because your code looks right and yet it's misbehaving. But that semicolon means stop looking for subsequent lines of related code. So if you do include it up top, the subsequent lines, even if you have these curly braces, are not in fact going to help you. So the takeaway for now, I would say, is this all safe for work? Yes? Good. The takeaway for now is really to look back at some of the examples we've seen in lecture, some of the examples you've now seen in the super sections and then the future sections, really for guidance. It's deliberate that a lot of the examples in lecture are fairly short and bite-sized so that you can actually focus on pulling out the key ideas without getting distracted by lines and lines of code. And I'll point out as we proceed, because I kind of have to start using the cloud here, it's your username that appears in these messages. So we'll say hello to you later if need be. So with that said, scary voice number 2. All right, so functions and return values. So just to hammer home this point, for now, a function really is like a black box. It's something that someone else wrote, or maybe you wrote, but you encapsulated all of your ideas or your functionality inside this thing called a function. And its purpose in life is to maybe take input and maybe produce output. But if it does take input, you have to provide it in the form of arguments or parameters, like printf takes, generally inside of those parentheses. And if it returns a value, you've got to do something with that return value too, much like we did up here. You've got to store it in a variable. You have to pass it as input to another function, as you'll see is possible in problem set 1's specification. But it's ultimately up to you. So let's take a look. If you still have your printouts for Monday, we have a couple of examples among those printouts. This one called return1.c. So in here, you'll notice a couple of key things. So one, a wave of the hand for the moment at this int argc and this char argv. We'll come back to that today when we introduce more formally the idea of arrays and command line arguments. But there's a couple of other curiosities. For some reason, at the top of this file, I've also included what I've called a function prototype. So we'll see in a moment why that's necessary. In fact, this kind of looks like a function, and yet here's a semicolon I just said can get you into trouble. And yet that's not actually a function because there's no interesting lines of code, because it turns out the interesting code is down here at the bottom. So it turns out that main, yes, is the default function you write, at least in C, when writing a program. And the computer just knows that when you run a program, it should look by default for a function called main, as opposed to one called printf or anything else, for a function called main and execute that one. And then it's up to you to call other functions like printf if you want to. Well, you don't have to just take what you've been handed in life, functions like printf or round, or maybe other functions you've seen in supersections or by poking around. You can certainly implement your own. Now, this is not a particularly compelling case just yet of implementing your own function. But let's suppose that I realize that I'm doing a lot of addition in my programs. And I actually want to factor out what seems to be becoming a lot of copy-paste. I keep seeing addition, and I keep just copying my code, copying my code. Anytime you find yourself in this pattern, odds are what you're doing is a candidate for being factored out. Hierarchical decomposition is the buzzword you'd see in the textbooks if you're following along with any of them. But it's really just the idea of taking out common code and putting it in just one place. So how do you define a function? We have to decide three things. One, the name of the function. And just as with variables, you should use some common sense, some style here. And the function's name should communicate what it does. Calling it x or y or z is generally not all that helpful. It then should take an argument or parameter if you want your function to take input, if you want it to take a so-called argument or parameter. There's a subtle semantic distinction between argument and parameter, but for all intents and purposes, they're the same thing. An argument or parameter is an input to a function. Now, in this case, it's clear that I'm not only saying this function takes an input, I also have to give that input a name. Because if I don't specify a name for this input, I have no way of actually referring to it in subsequent lines of code. Now, I seem to be violating my own mantra here by just calling this variable a. But this is reasonable. Much as with for loops, when you just call an incrementing variable I, because you just need an index, well, same here. If you're writing a one-line function whose sole purpose in life is addition, and clearly this is about addition, well, then it's in fact reasonable to use a shorter symbol like a. But I do have to specify its type. So here's where C differs from some languages that you might be familiar with, and from languages you'll see later in the course, like PHP and JavaScript. You have to be ever so explicit as to what data type you're actually passing in. So that's 1, the name, 2, the arguments or parameters, and 3 is the return value. So you're implementing this black box, and if its purpose in life is to actually return a value, you have to tell the compiler what kind of value to expect. And this is going to have ripple effects. If this function increment is defined as, or declared as we say, returning an int, you have to make sure if you're doing something with the return value that you're storing it in the same type of a variable, like an int variable, or you're passing it to printf with %d, that you're using it in the appropriate context, unless, as an aside, you intend to typecast it, which we've discussed briefly. All right, so what's the role of this function? What's the role of this function in life? It returns its argument +1. That's it. Now, it's a stupid little function. We could certainly implement this much more efficiently by just writing this one line of code. But again, the key here is to take this step toward decomposing our code into chunks of code. So much like you did with Scratch, some of you might have implemented these very unwieldy programs. And that's fine because you're kind of constrained in Scratch. You don't have these kinds of design capabilities to the same extent. But a lot of you did realize you can have multiple when green flag clicked scripts. And so you can factor things out to have different sorts of roles. So same idea here, even though in Scratch you cannot call functions that you yourself wrote. There's no notion of naming a script as you can a function in Scratch. So here's the main function. What does this thing do? Int main, let's ignore what's inside the parentheses for now. Int x gets 2, so that declares 4 bytes of memory and stores inside of them the number 2. This is just aesthetics. X is now placeholder. What do I place? The value of x. Now I say incrementing ... just to convey the idea of some progress. And now here is a so-called function call. We've seen function calls before. You've used getInt, getString, or the like perhaps already. Well, here I'm calling my own function, increment. It's defined later down, which is fine. I'm passing in x. and yet I'm also assigning the return value to x. So just intuitively, what's going to be the effect of this one line of code? Right, so to do x plus plus. So again, this is why I'm disclaiming that this really isn't all that interesting yet. But what am I doing? I'm passing as input the value in x, which is 2. I am then doing some mathematics with it, clearly, based on the below. I'm returning the result of that summation, so it's probably now 3. But when I get that 3 back, if I don't actually do anything with it, like assign it, it's all for naught. And so I decide arbitrarily here to assign it back to x. And so the end result, in this particular case, is indeed identical to saying x plus plus, but now we have the framework in mind, or the capabilities in code, to start doing more interesting things with functions like this. And actually, if I don't want to clobber, as we say, overwrite the value of my variable, I could declare another one and store the return value in y. So now I have 2 ints in memory, x and y, one with 2, one with 3. But in the end, because I'm taking this approach, if I proceed with the remaining 2 lines, it says incremented. X is now hopefully 3. And that should be a working program. So let's take a look. Let me go ahead and compile return 1. All right, everything seems to work. So let's go ahead and run return 1, enter. So it does, in fact, seem to work. But there's a key line of code that I glossed over a moment ago. And that was this one here. I have my include standard IO, so I can use printf. But then I had this thing called a prototype. Let me actually get rid of that for just a moment, resave my file, and actually now recompile with make. So now I've got an issue all of a sudden. I just reran make, or GCC, which does it for me. And now I've got all these errors. Well, let's see. In function main, all right, that's not helpful yet. OK, interesting. So here's a tip if you've not picked up on this already. If you're getting these compilation errors, well, when you compile, notice there's a number of helpful tidbits here. So one is obviously the file name that I've been working on. :21, though, for those already familiar, is so the line number, right? And Nano, though it's a primitive program, we've deliberately turned on a feature where if you scroll up and down, it literally tells you at bottom left what line you're on. So that can help you narrow in on the problem you're having. Well, what was that problem? Let me move it higher up. What was that problem? Implicit declaration of function increment. So here's where C is kind of showing its age. It's kind of a stupid lack of feature that this is the case. But notice that here's main at the top of my file. I like it at the top of my file. It's the first thing that gets executed. Makes sense to me logically that I want to see it first when I open the file. So I scroll on down. But only later is increment declared. So C, or the compilers for C, are kind of dumb by definition of the language years ago, whereby they only know about what they've already seen. So even though increment is obviously declared and defined in this function, it's later. So it's too late for me to use it in main. So I have 2 solutions here. One, what would be sort of the obvious sort of hackish or solve it fast solution? Right, just move it to the top, right? Delete those lines of code, move them up to the top, and problem solved. Now, downside of this, well, I've just now violated my preference for having main up top. Maybe that's forgivable, but very soon will you find that if you're writing programs with lots and lots of functions, and some might call these, and these might call these, you can come up very soon with scenarios where you cannot order them top to bottom because everything is commingled, and there's a lot of crosstalk among all your functions. So thankfully, C does provide a solution for this, whereby I can provide a hint, essentially, to the compiler. It's a little redundant, admittedly, but I include not the same function, but just its prototype, as I say in the comment here. What's the prototype of a function? The prototype is just its return value, its name, and its arguments, if any. But a semicolon thereafter is sufficient. You don't have to re-implement the function. You certainly shouldn't change anything about the function. So now, henceforth, when we say to declare a function, I am declaring a function here. But down here, am I, quote unquote, defining it or implementing it? And that's the semantic distinction. Yeah?
How can you name the function like int a, but it works for x?
How can I name it int a, but it works for?
Like it's x up here, but
Really good question. We'll explore more of this today, actually. But this choice of names, both for my functions and also for my parameters or my variables, is completely up to me. What's going on underneath the hood, as we'll see pictorially today, is that when I declare this x, this variable x here, right? I defined this last week as just a little block of memory and RAM. That represents 4 bytes, 32 bits, and the number 2 is currently in it. The fact that I've called it x is really just a programming it's a feature of the programming language that I, the human, can now refer to it not by some very arcane numeric address inside my computer's memory, but by a symbol, by a name. It's just more useful to refer to it by name. Well, I don't have to use that name for every copy of x. And as we'll see in a moment, when you call a function, what actually happens is that that function gets its own chunk of memory that's identical in size to the data type it expects, in this case an int, which means this function increment also gets from the computer its own 4 bytes, its own 32 bits. And when you call a function, one of the things that happens is whatever you're passing in, for instance x, and if this is a, this thing gets copied into a. So at that moment in time of calling increment, I actually have 2 copies of the same value in memory, but they're referred to by different names. But this is this raises a problem that we'll see actually in just a moment, having this duplication. But good question. So short answer, yes, you can use this for nefarious purposes. Not so much with ints, because ints are bounded in size. They are 32 bits or they are 4 bytes. But once we get to strings today and arrays, then absolutely, this is how a lot of software and servers are still compromised today. So putting back that prototype allows me to compile this because I'm saying proactively to the compiler, hey, you're going to see a function called increment. It returns an int. It takes an int. Deal with it when you get to it, and then once you've looked through the whole file, should you ultimately find the actual code that defines or implements this thing. Well, let's look at a slightly different version of this. So in return 2, we have a slight variant here where I'm declaring a function called cube. So let's take a look down here at what I'm doing. And notice here that this is perhaps more compelling. Right? Doing incrementation, pretty useless, right? Because I can just use plus plus. I could have saved myself 5 minutes of verbal discussion. But with something like cube, now it's starting to make a little more sense, right? Not to harp on the mathematical features of this, but cubing, if you're starting to do x star x every time you want to cube some value in a program, it just feels like this is going to get a little messy looking, if nothing else. And conceptually, the idea of cubing a value feels like you could package that up into a little box, a little tool that takes input, a value, and returns output, the answer, so you don't have to constantly do a star, a, and so forth. So this program, at the end of the day, is pretty much the same thing. I'm taking an input, I'm returning some value, but now at least we're a step closer to doing something that's a little bit more compelling. But this isn't always a good thing. So it turns out there's this issue of scope here. So when you define a function, you have, as we've seen, these curly braces that define all of the code that's associated with that function. Open curly brace code, close curly brace, that is the function. These functions thus far have been short. They've just added a number or they've multiplied a number a couple of times, but they've each had what's called their own scope. And by this I mean the following. If we go ahead and open up buggy 3, the clue already is that there is in fact going to be a problem with this. Because my purpose in life here is a little more interesting. For whatever reason, I've decided that I need to be able in my program to swap the value of 2 variables. All right, now I could do this pretty easily in just by reasoning through it, right? If I have 2 values, let me go on up here. If I've got 2 values, let's call it int x gets 1. Int y gets 2, semicolon at the end. So now I want to actually swap these values. You might think, in this board, you know what? Let's use the computer, because it will erase more cleanly than chalk. So we just upgraded. All right, so now we have int x gets 1. Oh, this is much faster. Int y gets 2. And now my goal in life is to swap these things. So now, at first glance, you might be a little lazy and be like, all right, well, x gets y gets x. Bug. All right, what's the problem here? The murmuring is correct, right? So x gets assigned the value of y, but then y gets the value of x. So what have you really done? Both of them now equal what value? So both of them now equal? I'll keep asking until we get the right, until we all merge on the same one. So what does the value have? So x is getting assigned 2. So now x equals 2. Then y gets assigned the value of x, which is 2. So I think they are, in fact, 2. Right? So you're clobbering the value of x, and then you can't get back x's value because it's too late. All right, so what's a quick fix? Well, we know how to declare variables here. So why don't we just have a temporary one? It's reasonable because it's meant for temporary purposes, just to call it temp or TMP for short. And I can define temp as, why don't I set it equal to x initially? Because now that I've stored x in a separate chunk of memory, I can now change its value. And then I can say y gets not x, but temp. And so now I've actually swapped these values. All right, so you can't do this because you're going to lose track of the numbers if you do that. You actually need to kind of do this. And then you can swap these two numbers, but it requires 50% more memory. It requires this additional int. All right, so suppose I want to do this a lot in a function. It's reasonable to assume that I want to implement a function called swap that takes two arguments, a and b, and its purpose in life is to swap those two values. Well, let's see what it does. All right, well, it looks like I just stole my own implementation, but I happen to call it a and b instead of x and y. And so here, what's going on? Well, one function is called swap. Takes a one int called a, followed by another int called b. And as we've seen with printf, if you have multiple arguments, you separate them by commas. Same deal here. Now void. We've seen void before. Void just means this function doesn't return anything. Its purpose in life is to do something, to have what we call a side effect, but it doesn't actually return a value because functions don't have to have values. They only need to have values if you care about getting something back for them. GetInt, you care about its value, but swap, I don't want to hear from it again. Just swap these two values for me and let me move on, is the reasoning. So here I say void. It doesn't return anything. So it would be incorrect to try to assign this to a variable x or y or z because it doesn't actually give me anything back. So this code is in fact correct. This code does swap the two values a and b. However, when I run this program, something happens. I first print what x is. I then print what y is. I then claim I'm swapping. I then perform the swap. I then insist, OK, swapped. And then I print out their values again. So in theory, I should see 1, 2, 2, 1. Well, let's actually see what I see. So let's go ahead and make this. This is buggy 3. There are no syntax errors, so it does compile. But if I run this thing, buggy 3, they've clearly not been swapped. So let's do a little sanity check, right? When in doubt, let me use printf for now. We'll use more sophisticated tools before long, but let's do a little sanity check. Let me go ahead and call printf. I'm going to say a equals, and then I need a percent d backslash n comma a. So this is a little bit of more syntax than would be nice, but I'm just saying literally a equals percent d, and I'm plugging in the value of a for percent d. So I have a little cheat sheet. Let me go ahead and do the same thing with b. So I have a little sanity check now. Inside of swap itself, I'm printing out the values, if temporarily. Let me go ahead and recompile. It works. Let me go ahead and rerun. So it does seem to be working, right? X is 1, y is 2. OK, it worked, right? A is 2, b is 1. And yet somehow the process gets undone. So it's almost as if functions really are useless because they have no ultimate effect. OK, so it's a good thought. Maybe the problem is that well, let's see. Here we're defining the function at the bottom. OK, so there's a couple of fixes. And let me come back to that one. So there's a couple of fixes here. But why is this problem happening? Well, just a moment ago, we did have, and this time I'll use some chalk here. A moment ago, we did have a picture depicting what was going on when you called a function. And so in main, if we call this the chunk of memory that main owns, main has, at this point in the story, two variables. We call them x and y, recall. And y2, well, I said int x and int y. So that gave me one square here called x, one square here or wherever called y. Done. 1 was put in here, 2 was put in here, and then I called this function swap. So swap, as promised earlier, is a function. It's given its own memory as much as it asks for. It asks for how much? Well, it's actually asking for three things. They're declared a little differently, but essentially this a and this b, even though we call them semantically parameters or arguments, really they're just local variables. So variables you were introduced to in Scratch, and there was this idea of global and local variables, but Scratch called them something a little different. When you created a variable in Scratch, you could either make it for this sprite only or for all sprites. All right? For this sprite only means local. Only this function, only this script can use this variable. Make this variable for all sprites meant it was global. But thus far, we've only been looking at local variables, which a and b essentially are, because they're defined inside of this function swap, and temp certainly is a local variable. So swap has 3 chunks of memory. It has a, it has b, and then it also has temp. And what happens the moment I call swap, as I said earlier, you get a copy of the inputs. Now, if they have different names, not a problem, because they're different they're the same types. That's what matters. So a gets 1, b gets 2. Now the swap function itself starts executing line by line. So I declare a chunk of memory called temp. I then store in it a. This makes a copy. So the assignment operator thus far makes copies of things. It doesn't move the value. It just copies the bits. And if the bits represent 1 here, those exact same bits are going to represent 1 here. So now the second line of code is a gets b, semicolon. So what does that mean? Well, a has to get whatever's in b. So now I'm clobbering, as they say, this value here. And at this point in the story, this is not good. Right now I have 2 copies of 2. But that's why I kept this thing around. B gets temp is the third line. So temp is here, b is here. That means 1 gets put here. And now I print out the values. They are correct, as the picture suggests. But then I hit that curly brace. And when I hit that curly brace, swap's role in life is over. There's no return statement. He's not actually returning any value. He's not returning a or b or temp, and definitely not x or y. So he just did all of this work, and yet that's it. What happens? The moment swap returns, it's as though this never happened. The computer essentially forgets about the memory that was being used here, here, and here for those 3 values. You might very well have done some very accurate math, but it doesn't matter because you did the math in the wrong place. So this issue of scope is to say that functions have scope. And when you declare a variable, whether as an argument or as literally a local variable, they only live inside of that function. And same deal in main. Same deal in main. It is not correct, for instance, for me to do this. You know, why am I wasting time passing things around? Why don't I just do this and be clever? Why don't I say int temp gets x? Let's say x gets y, and then y gets temp. This too would fail. It looks cleaner, right? I'm not wasting time typing out arguments and implementing more complicated function. I'm simply saying swap x with y. But this too won't work because where are x and y defined? In main, in a different scope. They live in this memory, whereas right now we only have access to this memory. So this is a good thing in principle for security. We're kind of restricting ourselves to only certain chunks of memory, at least for now. But it's certainly creating problems. Yeah? Indeed. So there is a solution, and that is the solution. So, but we will get there. In fact, as we introduce arrays today, we'll begin to see exactly how we can circumvent this. And what it's going to boil down to is moving away from just using these user-friendly labels, x, y, z, a, b, and actually looking underneath the hood at the numeric addresses, which we talked briefly about in weeks past, at how this stuff is actually implemented underneath the hood. Yeah? Initially, how come I don't have to declare temp as what? In which context? Oh, OK, good question. So up top, the function prototype. The only thing you have to put in the function prototype, again, is 3 things. 1, the name of the function, the return value, and its arguments. You don't have to mention any of the local variables, because at this point in the story, they're just not relevant. The only thing the compiler needs to know is kind of what pattern to look for in the rest of your code. And if it sees SWAP, open parenthesis, close parenthesis, and it hopefully sees 2 ints inside of it, that's all it needs to do in order to finish compiling your code. All the local variables can be dealt with later. Good question. Yeah? Why does it say void too often? So void, again, is my way of saying swap does not return anything. It doesn't return an int, doesn't return a float. You have to, with C, as with a lot of programming languages, say what you return. And if you're returning nothing, you don't just leave it blank. You say void. And that's the convention. Yeah? Sorry, what about curly? Good question. Is scope defined by curly braces or by functions? Absolutely by functions, but you can also create local scope with curly braces. And so what I was hinting at earlier, when you put semicolons in the wrong place and then proceed to have curly braces around arbitrary lines of code, you're creating a even more local scope there. which is generally not the intended behavior. It's a good rule of thumb. Yes, you can find ways around this, but a good rule of thumb is if you declare a variable, int x, string y, float z, inside a curly brace and another curly brace, you can only use that variable inside those two curly braces specifically. That's actually a really good rule of thumb. Well, things can be fixed via a little trick called global variables. It's not necessarily the best solution, but it is one solution, and it's perhaps necessary. And when we get to PHP and web programming toward the tail end of the semester, you will actually deliberately use what we call global variables to get access to any forms that the user submits. If you're actually implementing an application, a search engine, a web-based tool, a Facebook-like tool that takes input from the user, you'll be handed those data via variables like these. So what can we do to solve this? Well, let's go ahead and open up global.c, or you can follow along up here. So now notice this is almost the same program. I've got my function main. I then print x is now such and such, initializing dot, dot, dot. I now assign x the value of 1. But wait a minute. I've already written buggy code, it seems. What have I clearly omitted from main? So there's no mention of int. And yet we've been saying for the past couple of lectures that anytime you declare a variable, you absolutely have to specify its type. And here I am now cutting corners. Well, not quite. If you scroll back up on the printouter screen here, you'll see that you can actually not only declare functions prototypes, their general structure at the top of your file, you can also put variables there. You can put a variable there, and because it's not encapsulated in curly braces, as we just discussed, that essentially means it's accessible everywhere in that file. Any function in this file now, including main, swap, increment, cube, whatever I want to implement, now has access to this variable x. Now, that can be a bad thing. And you can very quickly take this feature to an extreme and start putting x and y and a and b and temp and all your variables up top, because it would seem to solve all of your problems and stop all of the thinking. But it's generally not a good thing, because when you start writing more compelling programs and start using libraries, other people's code, like the Google Charts APIs and things like this, if you start putting all your variables at the top of your file and making them global, well, what happens if you start integrating your code with other people's code? Things start to clash very quickly, and you have to go back to the drawing board and fix all of the collisions, all of the names that you happen to use, like X, Y, and Z, and Google happen to use, like X, Y, and Z. And so just very bad things happen quickly. And so you use globals sparingly. But how do you use them? Well, if you declare int x up top, you can certainly update x to 1 here. If I now scroll down to the actual implementation, now does this work or not work? So the hint is that this is our first program that's not been called buggy something, right? So it does, in fact, work. And yet, notice that the function itself, it takes no inputs. I say void to specify no inputs. You can also get away, as I said last time, with just putting parentheses. And in JavaScript and PHP, this is, in fact, the norm. In C, the truly correct way is to be very pedantic and say nothing is coming into this function. So I'll explicitly say void here. So this function increment takes nothing, returns nothing, and yet it does something. It does, in fact, successfully increment x, because at this point in the story, x was not scoped to main. It was scoped to the whole file. So pictorially, it's as though there's now some other part of the blackboard here, maybe way up here, where I can put anything I want that's accessible to main, that's accessible to swap, that's accessible to increment, or any other function I might implement, because it is, in fact, global. Why don't we go ahead and take our 5-minute break? All right. So I've got one more piece of bad code on this point, and this is buggy5.c. So as the comment atop this file challenges, what is in fact the bug? Well, let's take a look quickly together. So I start this program by declaring, as I did before, a global variable x. It is global simply because it is not inside any of my functions. It's instead outside of them, and by convention at the top of the file, so that I can access it anywhere. Whether or not this is a good thing remains to be seen, but it is a solution to this problem. I then declare increment early on, my prototype, again, so that I can use it later without the compiler wondering, what is this increment that you're referring to, because it's not otherwise been declared. As an aside, why are you able to use printf without writing out a prototype for it? Well, remember this line? include standard io.h when I said in week 1 that you don't actually have zeros and ones inside this header file, right? That's not actually where someone implemented printf and related functions. Rather, in .h files by convention are prototypes. So this thing called a prototype generally lives, if someone else wrote code that other people are meant to use, generally lives in these header files, whereas the implementation, the definition of printf, probably lives somewhere in a corresponding .c file. So somewhere there's standard io.c, somewhere there's standard io.h. But for me right now, the only file I need to know about is the .h, because what sharp include really does, it's what's called a preprocessor directive. It pretty much means open this file standard io.h and just paste its contents right here. Now, because among its contents is the prototype for printf, that is why, very simply, I can call printf without having to declare its prototype myself. So thus far, we've taken that for granted. Now, my main function here is identical, but here's a new and improved, I think, version of increment. Returns nothing, takes nothing, but it does perform plus plus, but I did something stupid. I did something that's allowed, but something stupid. So here I'm declaring another variable called x. This is totally legit because I already know that if I'm implementing a function like swap or increment, I can absolutely take inputs. I chose not to. I can absolutely allocate local variables. I chose to. This time I called it x. I hard-coded into it the value 10. There's still another variable in this world called x. Its value is by default, what did we say, 1? And so now there's two copies of a variable that there's two variables that happen to be named the same thing. But just as I've drawn them physically in different places on the board, if you think of this blackboard as a big chunk of RAM, your 1 gigabyte of RAM, your 2 gigabytes of RAM in your computer, this version of x is here, this version of x is here, and that's fine because inside of curly braces, can you redeclare variables with the same name if you intend to, quote unquote, shadow the previous variable. Now, for now, it's hard to argue that this is a good thing. But it's a common thing. It's a common mistake to make if you forget that I've actually declared that variable up top. But wait a minute, I know anytime I use a variable, I have to declare it. Well, this will, in fact, be declared. But unfortunately, you're using a different chunk of memory. You're incrementing this chunk of memory, plus plus, to 11. You do the math correctly. Increment returns, what's the value of this x at the end of the day? It's the same. It's still 1 because you plus plussed the wrong symbol called x. So for now, take away from this, don't do this. We'll see that there's actually compelling use cases for using the same names of variables in different contexts. Frankly, you'll see as a matter of design or style, sometimes it just makes sense to call the variable x if that's consistent with the type of code you're writing, or maybe just to come up with an arbitrary example, maybe if you have two parameters and you want to call them left and right, because conceptually in your mind, the purpose of this function is to do something with the variable that's on the left-hand side in the world and a variable that's on the right-hand side. You don't want to rename them L and R or X and Y because you want to call them left and right. Well, you can, but you have to appreciate the implications of doing so is the takeaway here. So what's really going on inside of memory? I've been using the blackboard a little ad hoc here, but suppose I neaten things up now and present to you this rectangle that's going vertically. This rectangle is, let's say, our RAM, the memory inside of your computer. This is different from the hard disk, which is where files and stuff are permanently stored. RAM is this memory recall, or as you'll soon find in problem set 1, that's used for ephemeral purposes. For when you double click a program, it's loaded into RAM. When you're working on a file, it's saving constantly to RAM, but also hopefully to disk, to the hard disk, so you don't actually lose it if the power goes off. Well, if this is now my RAM, what's really happening is that there is some organization to functions and such being called. By default, if this is my RAM, main itself can have parameters, as we'll see in just a moment. argc and argv, those symbols I've been waving my hands at, well, where are they located in memory? Well, memory is this rectangle. By default, they're located at the bottom. Now, they might not take up the whole width. This is somewhat of an artist's rendition, but they're at the very bottom of my RAM. Now, what's on top of that? Well, if main has any local variables, x or y or temp or foo or bar, whatever the case may be, those variables come next in memory. So you can think of it left to right, top to bottom, whatever. The point is they come next in RAM. Now, if you call a function like increment or cube or swap, or in this case foo, those variables or the parameters to that function end up getting stored next in memory. So everything is literally going back to back to back. And so foo, similarly, if you have any local variables like temp, it then goes here. So when I said earlier that as soon as swap returns, all of the memory allocated for swap is now useless, it just disappears, that's because this process unrolls. If you think of these kind of like trays in a cafeteria, right, that are kind of upside down, and by default they're stacked from the floor on up and up and up. Well, if you want to call a function, it's like putting another tray on that stack of trays, and that tray represents a chunk of memory that that function can use. Well, if that function calls another function, you put another tray on, and so that new tray represents that function's chunk of memory. But as soon as the most recently called function finishes executing, you have to take that tray off the stack in order to get at the previous function's memory. And once he's done executing, you have to take that one off, and then what's left? Well, then main. So even though we're not literally throwing RAM away, we're not physically moving anything, conceptually, we have to go through memory in this order, back to back to back, and then undo it. So pictorially, you can imagine foo getting called, and then it finishes running. So these rows in this chart would just be whisked away. The bits are still there, much like bits are still left when you erase a file on your hard disk, but they're forgotten about. So pictorially, this row would simply disappear. Now, there's a bigger picture here. I intentionally use this very common analogy of a stack of trays in a cafeteria. Well, because the memory we've been using for local variables and for functions storage space is what computer scientists generally call the stack. It turns out that slightly before the stack, slightly before this conceptual chunk of memory, there's other things called environment variables that we may see over time. But elsewhere in memory are other things. Text is where the zeros and ones that compose your file are actually stored. So when you compile a program called a.out or Skittles or whatever, and you double click that program, or in our command line environment, run it with /Skittles, that program is loaded into memory, just like Microsoft Word or whatever would be on your own computer. Where is it put in memory? Conceptually, it's put at the top of my chunk of RAM. Below it goes initialized and uninitialized data. This is a fancy way of saying global variables come next. And below that comes what's called the heap. So before long, we'll see, especially for problem sets, that we can't allocate an int every time we want to store something. Because what if we want to store 140,000 English words, right? We're not going to have 140,000 variables in my program. I need access to more memory, and I need it fast. Well, there's a chunk of memory called the heap that you can grab as much memory as you want, so long as it exists, for your program. But there's kind of a problem here. And this picture kind of makes clear that we're headed for disaster. Right? There's only a finite amount of memory, and very deliberately has that memory been laid out as such. So what's a problem we're probably going to run into very soon? Right? Stack, stack, stack. You're calling functions, 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 but you're allocating heap memory for your words. And eventually, stack and heap will collide. And one of the ways you can make a program crash, intentionally or not, is to essentially use up too much memory or call too many functions. And what happens is, bam, one hits the other, and bad things happen. In fact, let's see. Don't do this at home or on our systems. But let me go ahead and do nano don't do this .c. Let's go ahead and do int main void. Let's go here, and let's go ahead and say, let's call this foo. And what I'm going to do here is void foo. Foo, incidentally, is a stupid word that computer scientists use when they just need a placeholder. Mathematicians say XYZ. We say foo, barbaz, quux, and then it goes on from there. You'll pick up on it. Void foo. All right, it's appropriate to make fun. So what if I do this? This is kind of trippy, right? So main calls foo. Foo is declared, but wait a minute, I need my prototype. So void foo void. I just do a copy paste of that. Now there's a whole lot of foo and a whole lot of void here, but this is consistent with the lessons thus far today. Main calls foo. Foo calls foo. This is a problem. Right? Just conceptually, there's this kind of a funky picture that never seems to end. So let's see what actually happens here. I don't even need standard I/O because I'm not printing anything. I'm really just messing around with the computer. Let me go ahead and make don't do this. Looks good. OK, literally, don't do this. bad. All right, so segmentation fault. Some of you have actually had the privilege of having these errors already for different reasons. You probably weren't calling foo ad nauseum here, but a segmentation fault refers to segments of memory colliding. Two pieces of memory actually touching each other, or you touching memory that you don't actually own, in which case the computer doesn't really know what to do, and just bam, it terminates your program. And what very often happens if you do an ls in your account to list your files, there's a whole lot of stuff in here at the moment. And I don't have it here, but what you'll often see, I just faked this demo, is a file called core. If you ever see a file called core or something similar, that generally means you made a bug, and it's a pretty bad bug. And inside of core, as we'll eventually see, is the contents, or some of the contents of the computer's RAM at the moment your code screwed up, which is actually useful, because soon we'll start using a debugger, a diagnostic tool, where you can kind of do like an autopsy of your own program and see what was inside of it at the time this error actually happened. So now let's actually put some of these ideas to use in a more familiar way. So I've used this jargon before, command line arguments. But what does that really mean? Well, anytime you run a program at the command line like nano, you've almost always been putting one or more words after that program's name. Nano hello.c. GCC hello.c, and any number of mkdir for make directory, and then pset1 or similar. So all of these programs or commands we've been using thus far for the pset and in class take what we call command line arguments. They are the 0 or more words that follow the program's name. Well, thus far, I haven't written any programs that themselves take any such arguments, and yet it turns out I can do exactly that. If I don't write the shorthand notation int main void, but explicitly say, you know what, my version of main is actually going to take some command line arguments, and I want to call them by convention argc and argv, I can actually access input from the user without using getInt, without using getFloat, without using getString. I can get it directly at the blinking prompt, the command line. So here's a program called argv. This is fancy speak for our argument vector, our list of arguments, left to right. I have declared main as int main as before. Now, finally, I'm going to do something with this crazy syntax. Inside the curly braces is this program's code. What am I doing? I'm actually just going to do something simple first. Print the arguments to this function. I printf a \n just to pretty up the screen. I then iterate from I equals 0 up to argc. So argc is a convention. You could call it foo if you want, but shouldn't. By convention, it's argc because it means argument count. How many words were typed at the prompt? By default, argc should always be at least 1, because even though it's a little confusing or a little sort of contradictory, the argument count includes the name of the program itself, which can actually be useful because if a user changes the name of a program by renaming a file, you, the program, still have access to your own name via this mechanism. Now, what's this? Well, a while back I said that we'll use, at least for a few weeks, this moniker string. A string is a data type, doesn't really exist in C. It only exists in CS50's library. But I then revealed that this is actually, the word string, it's really just a synonym for slightly more interesting syntax of char star. Star, as a preview, is referring to what's called a pointer, similar in spirit, but more dangerous than references in Java, for those familiar. But we'll focus on these next week. This really is just a way of saying this is a string. The square brackets here, meanwhile, say this is a special type of variable that's got multiple values inside of it. So thus far, when we've declared an int and a float and so forth, we just put one value in there, the number 2, the number 3.14, just one single value. But we said earlier that we're going to get to the point where we want to have a lot of pieces of a lot of variables in memory, maybe 140,000 dictionary words for some future pset, but we don't want to enumerate line by line by line 140,000 variables. Turns out you can list one, give it a name, and if you use square brackets, that tells the compiler, I actually want to put multiple values inside of this variable. And how do we do that? Well, we'll see right now. So this for loop is pretty familiar. Argc is just an int, so this line of code here should be pretty comfortable by now. It just iterates from 0 to argc. The indented line here of printf is clearly printing a string, as per the %s. But what is it printing? Well, the bracket notation means you can index into this variable. You can think of this variable, argv, as literally an array, a sequence of chunks of memory that literally are back to back to back in memory. And when you say bracket 0, by convention, you are referring to the variable stored here. When you say bracket 1, you are referring to the variable here. Bracket 2, And how about if the array is size n, and I say bracket n, where am I referring? Too far, right? N is over here if we're counting from 0, so this too is going to be a common mistake. Last time I alluded to the exploit in the game Zelda for the Wii, where people were taking advantage of this and compromising the Wii system and installing their own software. It pretty much boils down to something as simple as this. That game uses an array for something, maybe Zelda's inventory or something like that. And the programmer who wrote the relevant line of code didn't check that the other functions are allowed, didn't check how far into this array other code is allowed to index into. So somewhere in Zelda is probably square bracket notation where it's bracket n instead of a maximum of n minus 1. So when we count, generally, again, we start from 0, we go to n minus 1. If you ever try to go beyond the boundaries of an array, as we'll soon see, bad things happen. So now what are we doing here? I'm first printing the 0th argument, which I said is the name of the program itself. I'm then printing bracket 1, bracket 2, bracket 3, bracket dot, 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 up until the total number of arguments, whatever that may be. And it's going to be at least 1 because the program always has a name. So let's go ahead and compile this. Make argv1. Seems to run OK. And now let's run argv1. Enter. Not all that interesting, but there's that new line I promised. There's the name of the program, including the dot slash. Well, let's make this more interesting. Foo. All right, slightly more interesting. Bar. Slightly more interesting. Baz. And now it's going to keep doing this ad nauseum until I hit some kind of limit. But for now, it pretty much will go up forever. But bad things will start to happen if I don't mind this lesson of indexing. If I do this, which is kind of a mistake we made last time, if deliberately. Let me resave this, recompile my program, and now rerun argv of foo and bar. OK, so that's already some badness happening. Now, why is that happening? Well, again, just as I said verbally a moment ago, if you're going here, you're literally touching, trying to read or change memory that's beyond the boundaries of the chunk of memory you're supposed to be touching based on its length. And in this context, the length of that array is stored in argc. Well, let's take a look at a slight variant of this that reveals further what we can do and reveals what a string really is. So here's a program set up in the same way. Main looks the same. I'm again saying print arguments, new line. I'm again iterating with this for loop. Same code as before. The only interesting thing now is a nested loop. So in Scratch block terms, I'd have a for loop or like a forever loop or something, and then another one inside. Same deal here. The curly braces ensure that everything is logically clustered where it should be. Now, what am I doing? I'm iterating on the outside from I to argc, 0 to argc. On the inside, I better not use I, otherwise bad things are going to happen. If I'm iterating from I on the outside, I on the inside, I'm going to start changing the value, and I might very well induce an infinite loop, but j is OK. So notice what you can do. And we've not seen this trick before, at least not in lecture. For int j gets 0, we can do that. Thus far, we always put what after the 0? In every example thus far, we've had a semicolon saying that's our initialization. You can actually initialize multiple things at once by separating them with a comma, and this is sometimes helpful. It turns out there's a new function that you've probably not used yet called strlen, S-T-R-L-E-N, or programmers early on and still like to be succinct but communicate sufficiently what they mean. So str length is the length of a string. Well, argv bracket 1 is in fact a string because I've said that char star is really just the true version of this. So conceptually, what is main being handed? It's being handed an array of strings. It's being handed a picture that looks like this. And inside each of these squares is a word, foo and bar and baz, as well as the program's name. But here, I'm just being a little more pedantic. That's really what a string is. We'll see why before long. So if argv just contains a whole bunch of strings, surely using this new square bracket notation, can I go to this string or this string, 0 or 1 or 2 or 3? But you know what? I want to know the length of each of those strings. Thankfully, someone else wrote a function called strlen that's given a string, given a bunch of squares like this, whereby each of them contains, given a string, sorry, let me retract that, given a string, argv bracket 1, it tells you how many characters are in it. If I type foo, I'll get back F-O-O. Now, here's the semicolon, j less than n, where n is this, j plus plus. So what am I doing? Well, it turns out with arrays, not to make this too trippy too soon, but if argv bracket something is a string, you can also use square bracket notation to go to a specific letter in a string. Because, little teaser, a string is just an array. When you've been typing in words to the keyboard like your name or any word that you're trying to provide to the user, a string really looks like this. It is a character of memory, 8 bits, 8 bits, 8 bits, 8 bits. And I've done the same picture on the board. So if a string is actually implemented as an array of characters, much like argv itself, or arrays in general, are just implemented as an array of strings, well, so can I iterate over each of the arguments, as I did a moment ago, but then also each of the characters in each of the strings. So argv bracket I gives me the ith string that I typed in. Argv bracket I bracket j gives me the jth character or letter in the ith word. So that's all we're doing. We're picking a word, and then we're homing in on a specific character. So what's the end result? Well, notice I'm calling printf with %c, and then I'm printing out each of these letters one at a time. And let's go ahead and make this. So this is make argv2. Let me go ahead and now run argv2 with nothing. Well, it's a stupid-looking program, but because I had more new line characters and because I was using %c for individual characters, 1 per line, now I'm seeing ./argv2. Well, now if I go ahead and rerun this with foo, I get this effect as well. So for now, a string is really just an array. It's a picture that, again, is literally like this. Somewhere in memory, back to back to back, are all of these strings, and with them can we store actual words and phrases. Now, why is this actually useful? So now that we begin to have this ability to express strings in memory and to understand what they are, we can start to apply actually real-world algorithms to them. So does anyone know or recall what this says? This is a sentence or string phrase that has been encrypted. It's been encrypted pretty naively, pretty simplistically. But it's actually an English sentence that's been somehow scrambled, but scrambled in a reversible way. If you just scramble a sentence, that's pretty useless because the recipient's never going to be able to reverse the process. So there's a pattern here. Think back to a movie that's on TBS ad nauseum in December called Christmas Story. Anyone? Little Ralphie? Yes, be sure. Two of us have seen this movie. So be sure to drink your Ovaltine. So Google it or look up the Wikipedia article for this movie. But in this movie, the kid gets a little secret decoder ring. Looks a little something like that. And the screen doesn't quite do it justice here. But there's 2 alphabets, A through Z and then A through Z. But the inner A through Z is on a it has a smaller diameter. So it's a ring of letters. Outside of that are the same letters, but slightly wider. And the whole thing rotates. So if you have A here, you can rotate the outer disk so that A lines up not with A, but B or C. So what you're seeing here is a very simple pop culture reference to something generally known as a Caesar cipher, derived from Julius Caesar, who purportedly years ago used to send encrypted messages using precisely this fairly simplistic mechanism, whereby you take a message you want to write, you then scramble it by rotating conceptually every letter by probably more than one place, but fewer in English than, say, 26 places, lest you be doing no work at all. You rotate the letters by a deterministic amount, by a fixed number of steps, so that the end result is actually something that can be reversed. The number that you choose to rotate your letters by is what we call in cryptography a key. It's a secret number, so that if Julius Caesar scrambled his message with the key 13, well, then the recipient had better know what that number is. Or, realistically, and this is why it's kind of hard to buy into some of these age-old algorithms, what would an alternative approach be to figuring out Julius Caesar's messages to his generals if you didn't know that the secret number was 13? All right, so trial and error. You can brute force it, and unfortunately, the so-called Caesar cipher is not very secure, because if you assume, for our purposes, an English alphabet with 26 characters, say all lowercase or all uppercase, my God, you only have to try like 24, 25, 26 possible rotations until you can figure out what his secret message is. So there are more sophisticated approaches, some of them mechanical. Those of you with backgrounds in history or who've seen or who remember World War II and technologies that were used in it might know of the Enigma machine, which is kind of the same idea. You type at the keyboard words that you want to encrypt. This was something the Germans used on their U-boats. And the output of that is a scrambled message. Here, the secret is not a number 13. It's actually the diagram, the details, the gears, and the handles inside of this physical machine that constituted a secret. So one of the things the Allies very specifically wanted to do in World War II was to hijack one of these devices, take it from a U-boat, because if they have this physical machine, certainly can they start decrypting then the Germans' messages. They don't have to know something in this case. They have to have something in this case. So in general, both of these are examples of what we call secret key crypto. This little picture here offers some jargon. If you have some plain text, some message that you want to send, well, you can encrypt it or scramble it using a key, a secret key, which might be a physical machine like the Enigma, or it might be a number like 13. But the catch is that the party on the other end of things has to have that same machine or know that same number. But this is a huge problem, right? Because all of us have probably bought something on Amazon.com or the like. All of us have probably logged into Facebook.com, passing your credit card information over the internet, passing your username and password over the internet. And as you probably know as a casual user, HTTPS denotes secure. There's cryptography going on. But how many of you have ever called Facebook up or called Amazon up and kind of whispered into their ear, I'm going to encrypt this with the number 13? Right? You have this, it's kind of a stupid thing, right? If you're doing that, it's a little strange. But the point is that how is Facebook, how is Amazon possibly going to communicate securely with you or your laptop using cryptography if you both have to know the same secrets? Well, this is a problem that we have solved and will solve in the weeks to come. See you Monday.